All right, we are going to cover 3.1, using graphs and tables to solve linear functions. So what's nice about this section is a review of Algebra 1. So hopefully this will jog your memory a little bit and you'll be able to review how we graph things, how we are able to see different viewpoints when we're doing these systems. So the first part of it is really nice. We're just going to verify that these are solutions. So what this is asking you to do is put this value of 4 in wherever you see x, and this value of 3 in wherever you see y, and to verify that those are correct. So if I take this first equation, I would now have 4 plus 2 times 3, and it's supposed to be equal to 10. So 4 plus 6, yes, it does equal 10. If I put it in the next one, we'd have 3 times 4 minus 3 is supposed to equal 9, so 12 minus 3 does give you 9, so it works. So an answer for this question would be yes, that is a solution for those systems. Okay, on our next one, again, we're going to plug in for our x value and our y value. So we'd have 6 times 5 minus 7 times 3 is supposed to give me 1. So I would have 30 minus 21. Well, that doesn't give me 1, so no. And if I try the next one, 3 times 5 plus 7 times 3 is supposed to give me 5, so that'd be 15. Plus 21, no, that doesn't give me 5, so that doesn't work. So as soon as it doesn't work in one of the questions, the answer is no. Okay, it has to work in both of them, or again, as soon as one of them doesn't work, then it doesn't. Okay. All right, solved by graphing. So this guy is a little bit different. We are actually going to take and make a graph, but before we can make a graph, each of these equations must read y equals first. Okay, so on that first equation of 2y plus 6 equals x, I need to get stuff away from the y. So I'm going to minus the 6, giving me 2y is equal to x minus 6. Divide both sides by 2. And it looks like I have y is equal to, when I simplify that fraction, it would be a half x minus 3. So there's the first equation I'm going to graph. And on that second equation, it's actually even easier. You're just going to minus the 3 minus the 3. So that guy is y equals 4x minus 3. Okay, so when I go to graph this, I'm going to make myself a little graph. All right, so I'm going to do that one in green first. It says I have a y-intercept of -3, 1, 2, 3, put my dot. I have a slope of a half, so up 1 over 2, put a couple dots on there, go backwards. Okay. There we are. All right, and when I do the second one, I have, a y-intercept at -3. Interesting. Okay, and a slope of 4. So up 4, 1, 2, 3, 4 over 1. Up 4, 1, 2, 3, 4 over 1. I probably even have room to go backwards. 1, 2, 3, 4, and down 1. So there's my second line. So this one was actually really nice because they share the same y-intercept. So the answer on here is 0, -3. When we graph them. Okay, so it's again where the lines are hitting each other. All right, next one. All right, so for that first one, I'm going to move the x over. So I would have y equals x plus 5. All right, if I do the second one, I'd have to move the 3x over. So I'd have y equals -3x plus 1. All right, so let's get those guys graphed and see where they hit each other. All right, so for that first one, y-intercept of 5, 1, 2, 3, 4, 5 dot. And our number in front of that x is 1, so our slope is 1, up 1 over 1, up 1 over 1. And I'll build my graph backwards because I just don't know where they're going to hit each other yet. Okay, graphing the second one. On this one, we have a y-intercept of 1. And I have a slope of -3, so I'm going down 3, 1, 2, 3 over 1, down 3 over 1. I can build backwards, up 3 over 1, and there I can see where I've hit each other. Oops, sorry about that, not a straight line. All right, so where they hit each other is right there, which would be at the coordinate point -1 and 1, 2, 3, 4. There we are. All right, classifying our systems. All right, so that means, do we have one solution, do we have no solution, or do we have infinitely many solutions? All right, so when you're classifying these systems, first thing is, again, let's use the same strategy as when we're graphing. Let's get them into y equals, please. All right, so I'd have to minus the 2x minus the 2x. So that first one would read y equals negative 2x plus 3. Okay, if I do that same thing to the other one, probably takes me a little bit more work. I'm going to minus the 9, giving me 6x minus 9 equals negative 3y. Divide both sides by negative 3. So this guy, we're going to have y equals negative 2x for my slope. And this guy would give me plus 3. All right, so when you're comparing the two lines that you have right here, we have exactly the same slope of negative 2, and we have exactly the same y-intercept of 3. So those lines are identical. So if we were to go to graph these lines would just graph right on top of each other. I guess I can do them in the different colors. They'd be here and here. So when it asks you how many times do they hit each other or how to classify the system, since they're hitting each other over and over and over again, the answer is infinitely many solutions. Okay, exactly the same lines. Okay, now the only difference would be is if we had lines that were parallel but didn't hit each other, that would be no solution. Okay, so again, parallel, meaning they have the same slope but different y-intercepts. That would be no solution. They don't hit each other. Versus if they were ones like we just did, they're going to hit each other once. So your only choices are one time. Okay, so different slopes on there. If they have the same slope but different y-intercepts, then we'd have no solution. Or if, like what we just did, they are exactly the same line, then it would be infinitely many solutions. All right, so our story problem today is going to come from page 185. I just took a picture of it on here. So we are comparing the cost of long distance calling cards. To use card A, it costs 50 cents to connect and then 5 cents per minute. To use card B, it costs 20 cents to connect and then 8 cents per minute. For what number of minutes does the cost amount to being the same for a single call? All right, so I'm going to write equations for each of them. So I'm going to call this card A. So my equation for card A would be y equals, it says it costs 50 cents to connect. So 50 cents just right off the bat. And then for every minute I'm on the phone, it would be 5 cents. Okay. All right, for card number B, we'd have y equals, and it says it costs 20 cents to connect, but it is 8 cents per minute. Okay. Now we want to know when these are the same. So in your textbook, it gave you the choice to make a table. Okay. And you can make some tables and start plugging in some values and seeing when they're the same. Okay. Now what we're going to get into in the next couple days is that if you have an equation that's equal to the same thing, then you can set the two equations equal to each other and just do basic algebra and solve for it. So I'm actually going to show that method versus the table. Okay, again, the book shows how to do the table because it's actually sort of faster and more efficient. So because they're both equal to y, I'm going to set them equal to each other. Equals 20 cents plus 8 cents per minute. I am going to move the 0.05x over. Okay, so minus 0.05 over here. So that would give me 0.03x. And I'm also going to move, so since we move this guy, I'm going to move the 0.20 over. Okay, that would give me 0.30 right here. Divide both sides by 0.03. All right, and I'm going to get x equals 10. Okay, and it says for what number of minutes does it cost? So we're going to put our unit on there, minutes. It would cost 10 minutes. I think that's a little faster and a little more efficient than making a table, but both methods work at this point. But I am going to be pushing you to do the algebraic method.